Good morning, Maren. Toddy, not Toddy, but today. Okay, we'll give it a couple of minutes just to make sure somebody else doesn't want to come before we begin. So why can't I see my... means I'm not sharing it. I thought I was. Try again. Better. And then, yeah, okay. Okay, let's begin then. So we're going to look into supervised learning today. Yesterday we did regression. So as I say in the note there, as we go through today, try and make links in your mind back to the work we did on supervised learning on our classification. which involved petals on flowers, and we'll begin. So first thing we need to do is to import pandas, which is the first line, and then get all of these GitHubs, which contain, firstly, that's the problem with long titles. So that is the Python program for doing our graphing. That is the optimizer from the machine learning library. And then lastly, our data, which is for Seattle weather, 1948 to 2017.csv. So they're the three things that we're going to need today. Initially, we're going to load that using the pandas read CSV function. So you'd address that as pandas.read CSV. That simply reads a CSV file, comma separated variable file, value file into a panda array. And that's what that first thing does. And it's parsing dates. So we're making parse dates to be equal to the date column. Okay, so we've made a variable parse dates equal to the date column. And we're going to keep only the January temperatures here. So the dates dot month we're setting for 1, so that's for January, and that's for all of the dates in the data dot date, which is our data file with the date extraction function in there, and copying that back. So we'll end up with only the January data in this variable here, and print the first and last few rows, which is the normal thing we do to check. You can check any kind of printable array using just typing its name, and it will give you the top and bottom. Now it's going to ask us, I'm sure, to open the sandbox again when we try this, but if we try this all together, yeah, we have to activate our sandbox. Hopefully it will do it automatically. Let's try again then. Yeah, didn't have to put in my ID that time. It's running the job. And we'd expect to have the January information printed out nicely. And here it is. So this is the January information for the first 5 and the last 5. These are the dates. First one starting from January the 1st, 1948. And these are all the ones for January. I guess they thought that would be the typical month to investigate this kind of data. Right the way up to 2017, and whether or not how much rain there was, what the maximum temperature was, the minimum temperature was, and whether it did in fact rain. So for example, if the rain was false, you would expect precipitation to be 0, and that is indeed the case. Okay, so no rain, you're going to get a false here. Okay, so 217 rows by 5 columns. That's describing the shape of the data. And that's printed for us automatically. Okay, let's move on. So we've got our data there. We'll analyze the relationship between date and daily minimum temperatures. So that's what we want to do. We want to see if there is a relationship here between date and minimum temperatures. We're trying to work out what we can classify by, you see, that's what and why we're investigating the data. So if we take a quick look at our data, as a graph. So here we have to import graphing. So this is our code that we brought in, our Python code that we brought in using the get in the previous code block. So we're asking graphing.scatter. So it's asking for a scatter plot in 2D of our data using the label on the x-axis to become date and the label on the y-axis to become minimum temperature and the title to become January temperatures. Okay, so let's run that. Okay, so there's our January temperatures, and as you can see, the minimum temperature is actually in a range there from around 5 degrees Fahrenheit there, possibly, up to a maximum of up here, up to 55, 53 there, 53. So we've got 53, and then we've got one there about 6. So there's our range. Now, these a lot of these transformations that we're going to use don't like to have asymmetric ranges like that. They like to work around a mean value and go plus and minus around that mean value. It kind of makes calculation of errors a bit easier if you do that. And that's one of the reasons why it's done. It also enables you to zoom in on particular areas of a graph by stating that you're looking for mean values of plus and minus, so on, a particular value, and then you'll see those values come up. So it enables you to process the data better, and that's what we're about to do now. So machine learning works best when X and Y have axes roughly the same range of values. We'll see why later. But for now, let's just scale our data slightly so that we can get plus and minus a range over here instead of a complete range from 0 to a maximum. Now we'll just to zoom in on the data a bit better. So this scales and offsets the data slightly, which helps the training process. Now the reason why you want to offset it is because at the lowest value here, your usable value, is around 6. So therefore, it doesn't make sense to show anything less than 6. Yeah? Same thing here. Highest value here is 50. So it doesn't make any sense to show anything more than that. So we can scale it by just subtracting. So if we subtract 6 as an offset, then all this wasted space down here, which isn't showing us anything at all, will now be a useful part of the graph. That's the reason why we do that, so we can better see what it is we're about. So that's what this does. The offset gives us our offset here in number of days, and we can scale and offset together and ask it to plot again. So let's do that. We went through this yesterday, and NumPy is obviously functions to do with number operations on the arrays. Like for example, mean data is a NumPy function. Yeah, there you go. NumPy provides. It shows how to use it. It's a module within it. Let's run it, and we should see slightly better data here. Firstly, we're now working around a mean, and we've got nothing, no dead space here. This is our point here, and our nearest value here is the next one down. So there's no dead space in the graph. This point here is what decides the lower limit of this graph. And it's the same thing here with the upper limit. There's not much dead space above the graph. So we're using all the space that's available in that direction, which really helps. And we're operating around a mean value now, wherever that mean value is, and we're plotting our points around that point. So now we're going to select our regression model. This uses a line to make the estimates. And we've seen trend lines like this before, where we're trying to find the two parameters. Two parameters are the slope, which we have to multiply the data by. So we always return the date, which is our data, times the slope, plus the intercept, and that will give us our prediction of our temperature. So we put in a date and we try and predict the temperature. Create our model ready to be trained. That's what we did before. And we just print the model out. I won't go through this again. We went through that before. So what we end up with is the model's made. So we wouldn't normally use a model before it's been trained. But for the sake of learning, let's take a quick look at it as we did yesterday. So this is our model parameters before training. And of course, this would come up with, for our intercept, 0 and our slope 0. Why? Because that's what they were initialized to in here, in the initialized part of that class declaration. So that's where we are there. Oh, good morning, Ritu. Good morning, Fahima.
Good morning.
Sorry, I wasn't looking at the chat, sorry. And so there we have it. Let's have a quick look at that now. And of course, it will show 0 and 0. So yeah, model parameters before testing is 0, and before training, we don't have anything as yet before training. So let's move on. Again, we then introduced yesterday the cost function, the idea of the comparison between the predicted value and the ground truth, the actual value. Okay. We see that the red line obviously isn't very useful at all, because the red line is going to give us data times 0 plus 0, which is always going to give us a 0 line. So if we take in a date, whatever that date is, minus 30 around the month or around the time, the years since 1982. So 1982 being the median year, the mid-year there, that's our mid-year. And then we go back to 1934, so we go back to 1948, and then we go up to 2017. Okay, so but our median year we're having here is 0, and our 0 year is 1982. That's what that calculation was doing before. And we can see that red line corresponds precisely to what should happen with the model parameters before training, 0 and 0. Okay, so the next part of the code with supervised learning compares the model's estimate to the correct answer. In our case, our label is temperature. So our cost function will compare the estimated temperature to the temperatures seen in historical records. That's what this is about. So for each data point, it will estimate what it thinks the temperature should be according to our two parameters, or slope and intercept, which is initially set to 0, 0, and it will calculate a loss function. And then we have to consider what we do with that in terms of optimizing the model. So this user-defined function here is cost, and it takes the actual temperature and the estimated temperature. So we pass those two values in, and it will return the difference and the cost, where the cost is the sum of the difference squared. Okay, that's what that means. And that's effectively our error that we can feed back because if our model perfectly modeled all the data, the cost would actually be 0. But this sum is the cumulative sum through all the data points of the cost. Okay, so it's the total cost, the total error in our model as it now stands against data we know the values of. So once we know that, we need to optimize that in some way. Let's just run this first. And you can see that if we look at this, we don't print anything, we just return it. So we wouldn't expect to see anything visible here because nothing's being printed. But running that function simply returns the cost, the difference and the cost, sorry. Then we need to consider the role of the optimizer to guess the new parameter values for our model. So we know the values aren't 0. Well, we don't know that. The cost is at the moment quite high, which we can see in a minute. And we can try and reduce that cost by changing those parameters. How they're changed is part of the algorithm, which we'll get into a bit later. But we just know that this optimizer, this is the library there. We're going to import this module, myOptimizer, and then create an instance of that in here. So we have our own version of the optimizer, which is of type myOptimizer, which has particular fields and functions. And we have to put these into a training loop. The purpose is to be able to loop around, changing our values of those two parameters, measuring the overall cost, and stopping when the cost stops decreasing. Okay, which means you're probably overshooting some function somewhere if the cost suddenly gets worse. So this returns a Boolean as to whether the training should continue, and the cost calculated, obviously the smallest numbers are the better. And the criterion for using the model is here, model.predict of our model inputs, and our model inputs are, go back up here. These are our model inputs. This is what we're putting in. And these are the true temperatures. So this is our ground truth. And this is the last value of the cost, because we're going to iterate through this, which means repeat over and over again until the cost gets reduced below a certain point. So obviously, in order to be able to do that, it needs to be able to know what the previous cost calculation was so that it can make a comparison as to whether to continue. And that comparison is made down here. To decide whether to stop continuing is if cost is greater than or equal to last cost. So we take the parameter last cost, which is passed this time for this iteration, and then we compare the current calculated cost. And if it's greater, then we should stop because the situation is getting worse. So we return false and the function ends at that point, meaning we return false. So to say we're not going to do any more training, and then we return the final cost to the calling function. Else, we continue to update the intercept and the slope using the optimizer based on the model inputs and the current cost. So this is the one that's doing the work. This line here does all the work of updating our first parameter, which is the slope, and our second parameter, which is the intercept. That's what's happening here. And then we can then change those model parameters according to the slope update, which is being produced, and the intercept update, which is being produced by the optimizer. Okay. And then once we're done, we return in that else loop, we return the true and cost, which means that we're still running at this point because we haven't just stopped because of this test here. And so at that point, we want to return true, so to say we're still running. and the current cost. And of course, that current cost gets put back into last cost at the end. So we keep going around and around and around. So let's run this. And then, of course, we played around with it manually.
Maybe we can run the loop, because here something has to call this function.
Yeah, that's next, I think, running the loop, isn't it?
Yeah.
So that simply says that the training is ready, which means we've been able to update. We've not got any data to update it from as yet. So the first estimate is going to be the same. And now we run a few manually iterations so that you can watch how the training works. Run the code following several times and show how the model changes. Well, we did this. And we run it first, and we got, let's have a look. Optimizer is not defined. That's not good. Oh, I know what I didn't. I didn't run my optimizer code. This one. You need to run that. Then we can run this. And then we should be able to run this. Hopefully without getting errors. Yeah, there we go. There are our parameters. Initial parameters are 0, obviously. And after the first iteration, we've just given the intercept a little bit of a nudge. That's what we've done. We now got 0.01. So, and then we can simply run this again. I know we played around with the code yesterday to make it print out. But as you can see, code is now getting better because it's increasing now the slope. A minus slope, that's interesting. A minus slope means the line goes the other way than you would expect it. Instead of going from the origin outwards, it now goes from the highest Y point downwards, because the slope here is minus, which kind of makes sense if you think about the data. Be good to be able to visualize that, wouldn't it, as it was running each time. And what we did yesterday was to extend that and play around with it, getting it to do this kind of stuff automatically and print the values out for us in a row. But we're not going to go through that again because we need to move on to the next step. So let's run this again. So it will take thousands of iterations to train the model. So let's just wrap it all up in one loop and we should get the end result. When it's done, and the end result is it's done lots of iterations, training is complete, and the final values are minus 0.006 and 0.0119. So let's see if that makes sense in terms of our data. There we go, that's our line. And as you can see, the intercept here, which is this one here, is, I think the sign is the wrong way round, because the intercept is definitely negative and the slope of this is definitely positive. So the optimizer, as far as I can see, made a small mistake. I think that should be a plus and that should be a minus. Because if you think about it, the intercept is below 0. Graphing's not as good as I hoped. And the slope is saying the slope looks about right for 0.0006 in terms of how much of an increment. Oh, okay, I got it. It's because that's a minus and that's a minus, which means, yeah, because we're talking about here, interesting.
X, maybe X is also 0?
Yeah, that's the point. the point here is that because this goes from minus to plus, you have to consider that the slope, the slope really should be the change in change in y divided by the change in x. And the change in y on this line here, if you look at it, is definitely, because it's starting below and ending above, the change is actually negative. Okay, so the change in y here it's a negative change. It's going from minus here all the way up to a plus point. So the change is usually done by the y value here minus the y value here, which in that case is going to be a negative number. And the intercept, so that's why that is a negative slope, is because we've got negative values here. If this was all positive and this was all positive, then that would be a positive slope with a positive intercept. It's because of our data is like this, that in order to get from our x point, which is here, to our y point, which is there, it's our y value, we need to apply this and this in each case. Okay, so that's looking at the graph. We'll look at that a bit more in detail later, but at the moment we did the summary there. We split up the data, and now we're going to look at minimizing the errors more with the cost function. So you read that yesterday, and we're going to use a cost function. And we'll see how that works. So we can look at different cost functions. Let's have a look. Oh, we've still got some sandboxes left. So again, let's load the data, make the exercise simpler. We're only going to use a few data points so we can zoom in. And these data points we're putting in specifically here. This is so we can really understand the process of the cost function. So as before, we get all the things we need to get, including date time. So we need to be able to understand the format of date and time. We load our file, which is this one, and we're still looking for date as our main column there. These are the values we know. We know the dates. We want to take information we know and predict some other information based on the trained model. Okay, but the data we know is this, so that's what we're going to parse and take out. And we're going to convert those dates into numbers so we can use them in our models. Now, the reason for that is that a lot of models only like numbers. They will not like June the 5th or something like that. It's not something they can do. If you try and subtract October the 21st from June the 5th in some kind of machine learning model, it simply wouldn't know what to do. It doesn't know what June the 5th means. It doesn't know what October the 21st means. But if you encode that in some way by saying June the 5th is all of the days from January the 1st and October the 21st is all the days from January the 1st, then you've got two numbers. Then you can subtract them and you can find means and all sorts of other things. But it makes no sense to try and find the average date of something when it's in a format of the 21st of October or the 5th of June. It makes no sense at all. The system would simply actually say NAN, not a number, and then it would stop and other things would crash. So you have to put them in formats that the machine learning can understand, and that's numbers. So what we're going to do here is to convert the dates into numbers so that we can use them in our models. we make a year column that can contain fractions. For example, 1948.5 is halfway through the year of 1948. Okay, so that's what we've done here. As before, we're taking a data set for year, dividing it by 365.25 for the days in the overall data set of data. Now that's what we've actually brought in. Okay, that's the data set here. If you look at this, data set is what we've read in for dates, and that's in here. And then what we're going to do is we've now converted our dates, our date format, into a number which says it's up to a certain fraction. So we're allowed to use fractions now for parts of years. So let's look at February the 1st for the following years. So this is a simple view. We're not going to load in the dates anymore for the moment. We're going to specifically convert these values here. So the desired dates are date time. If you look at the variables you can take in here, we've got year, which is 1950, month, which is February, and day, which is the 1st. We don't put in hours, minutes, seconds, microseconds, or anything else. We just put that in there, and we actually then will get a format. And once we see the data set, if there's a test there saying if the date is in the desired dates, which is these ones. So what it's doing is then is from our data set taking the ones that are within, that coincide with these set here, and making it the new data set. So it's a very, very serious filtering that's going on. So let's print it out and have a look. Okay, so let's have a look down. So we'd expect the limited number, is it 10 dates there, but put in a number format. That's what we'd expect. Why did it not print those out? Data set. Must be down here. Yeah, there we go. So it's taken our 1, 2, 3, 4, 5, 6, 7, 8 values that we put in here, and it's converted year now into a number. And the number is the year, and then the fraction of the year that you are into it. Okay, which in this case is all the same. So that means we're all looking on the 1st of February. So we're looking at the 1st of February. Let's check that. Yeah. So all the dates are the same. So you would expect them all to convert to the same number in terms of the year. Hopefully that makes sense. This column now has been translated from the dates, the real dates, into a fractional date, which the system can now handle. And we can now look at some specific cost functions. Let's compare two common cost functions, the sum of the squared differences, SSD, and the sum of the absolute differences, SAD. They both calculate the difference between each predicted value and our expected value according to the model. The distinction is simply SSD squares that difference and sums the result. SAD converts the differences into absolute differences and then sums them. So this gets the idea of converting them into absolute differences, gets around this negative sign, positive sign issue. It actually is measuring the absolute differences, the distance from the data point to the trend line. That is the absolute difference. That's the Y value of the data point minus the Y value of the trend line, but then you do the modulus of that. So you remove the sign. So you take the absolute value. Absolute value means ignore the sign. That's what it means. So that's what it's doing. So because that makes sense, because if you don't do that, if you get data points that are either side of the trend line, even though when you sum them all together, you could end up summing all of those to a 0 error result, when in reality they are all over the place. It's just that some of them will cancel out totally with one of the others and give you a lower result than you might expect for error. So it depends which order you do things in. You either square the difference, sum the result, or square the differences into their absolute differences and then sum them. Either way, you need the total, the sum, and that's in here, numpy.sum, of all of the errors due to the data points being different from the trend line. And that's what we're about, and that's what this does. So this does the sum of square differences, and of course you can see that's the calculation, numpy.sum of the estimate minus the actual all squared, or you can have the differences is the estimate and the actual, so we're returning here of the absolute value of the estimate minus the actual. Intuitively, this kind of makes sense, but it really suffers when you have outliers, because they can produce very large errors, and it's useful to know when you square these errors, if they're decimals, you see, if they're decimal points and you square them, the number gets smaller. So you can actually see better localized outliers, values that are further out come closer in that situation. So, and it's equally valid. And if you've done any statistics, you will know which one to use at which time. But as we don't know what the data sets are, we've done both here. So they're very similar. Let's see how they behave. Let's test them with some fake model estimates. Let's say that the correct answers are 1 and 3, but the model estimates 2 and 2. Okay, so we can now use this to apply. Oh, let's do it here. So it now understands, it has the user-defined functions which we've designed of sum of squared and sum of absolute differences. We've got that in here, and we're going to run that. So for our two values, we see that the SSD and the SAD are the same. Okay, and it's because we're really talking about numbers that are very close to each other. Hopefully we might do one that's a bit further apart to show the difference. So we have an error of 1 for each estimate, and both methods return the same error. Okay, because we put in a 3 and we got out a 2. The actual label is 1, 3. And so we put in a 1 and we get a 3, and we get back 2, 2. Because we got our estimate. So that is comparing the two. What happens if we distribute these errors differently? Let's pretend that we estimated the first value perfectly, but we were off by 2 for the second value. So what we're doing here is actually hard coding the result of the prediction, just for simplicity's sake. So we've got the actual label here is the NumPy array 1, 3, and the model estimate, which would normally come from our optimizer, but in this case we're going to hard code it, is the NumPy array 1, 1. Okay, so what we're doing now is we have a difference of 2, don't we, in here. And let's see what that does now to the different algorithms. Yeah, so now the SSD is 4 because it's involved in squared quantities, and the SAD is 2 because it's involved in absolute quantities. So you would expect that to be the case because we're talking about an error difference here of 2 on that data point. Bear in mind, we're only doing one data point. This thing really comes to its own when you're doing lots of data points, but we're trying to analyze the different method of using the error method. And we can see that for a simple difference of 2 here, the absolute sum of the absolutes obviously is 2, but the sum of the squared differences is 4 because the differences is 2. Square it, you get 4, and we've only got one value, which is why it's staying that way. So as it says here, the SAD has calculated the same cost as before because the average error is still the same. 1 plus 1 is equal to 0 plus 2. According to the SAD, the first and the second set of estimates were equally good. By contrast, the SSD has given a higher, worse cost for the second set of estimates because we're dealing with squareds here. We started off with a 1 and we ended up with a 4. So when we use SSD, we encourage models to be both accurate and consistent in their accuracy. So we have to, with SSD, if you do get a value that's a little bit off to the side, its effect is squared. Okay, so you have to be careful with what modeling you're using. If you're confident in your modeling, then you can afford to go to a squared model format. So let's compare how the two cost functions affect our model fitting. First, we'll fit a model using the SSD cost function. So that's the first one using the squares. Hopefully we can just call that function. Yeah, there we go. Cost function, sum of square differences. That's what we've got in our previous code block that we've used here. And then we're going to graph it. So let's have a look to see the result of using the SSD on our plot. So this is a plot of label of year against minimum temperature for that year. So that's the minimum temperature on the 1st of February for every year. That's what this is going to give us. And it enables us to, using the trend line, to find values that we don't have numbers for. But that's interesting because actually we have numbers for all of the points. So that is interesting. That's the data, and it's saying the minimum temperature is predicting an absolute minimum temperature for each year that you specify. So it's predicting what temperature you might expect. 1950 seemed to have been a particularly cold year based on our information. And then lastly, the sum of our absolute distances. Our SSD method normally does well, but here it did a poor job. The lines are far distant for the values for many years. Notice that the data point at the lower left doesn't seem to follow the trend of the other data points. 1950 was a very cold winter in Seattle, and the data point is strongly influencing our final model, the blue line. So, as I said before, anything that's slightly off the line, its effect gets massively multiplied, and it pushes the distance from that data point to the trend line in each case, or redraws a trend line. So let's try it with our absolute differences. So we're going to fit the model with our SAD function. And again, we've got here not the sum before we had the sum of the square of the differences, that function we defined, but now we're using the sum of the absolute differences, which is the other function that we defined. So let's run that, and then we're going to scatter plot that. And that's much better, because you see the 1950 result is still way out, but because we're only concerned with the sum of the absolute differences to the line, it quite sensibly let this one stay. It didn't try, it tried to minimize this distance, total distance here. And obviously in this point as well, but it certainly said, I'm going to declare you as an outlier, really, and not take much account of what you're saying. Now, interestingly, if you removed some of these data points, the trend line would start to move down towards this other point. It's because there are so many of these that can be drawn with a minimum error here by getting the prediction correct, that we can not do anything much about this line here. So, as I say, it's very good. If you can control your data and you know it's within a very tight range, then the squared gives you more visibility. If you know you've got data points that are a bit wayward, then you reduce their influence by using SAD and not the SSD, the sum of the squares. So it's clear the line passes through the majority of points much better than before, at the expense of almost ignoring the measurement taken in 1950. In our farming scenario, we're interested in how average temperatures are changing over time. We don't have much interest in 1950 specifically, so for us, this is a better result. In other situations, of course, we might consider this result worse. So yeah, especially if we were expecting a cold winter. So this is the output. This red line here is the output of our model. With this line, we can put in any year and we can get back what the average temperature is. It's interesting that because of this variation, there is a kind of, and because we're using SAD and not the absolute difference here, there is a tendency to make this line almost useless, if you think about it, because it's actually predicting a variation in temperature in total of a couple of degrees there and a couple of degrees there. So as far as this is concerned, the model is only worthwhile over a range of about 5 or 6 degrees. And we know, of course, that doesn't really happen. So I'm asking myself, if I'm a farmer and someone said to me, over the last 50 years, temperatures have varied by at least 5 degrees, and they're likely to vary at least by 5 degrees for the next 10 years or 100 years, I would say, why am I paying you? You're not really telling me anything useful there. You know, if your prediction suddenly, for some reason, changed the slope or had some other variation in it, then I might pay you. But you've not actually told me anything useful at this point, I don't think, because that slope is almost straight. It's almost flat. There's a very small variation in absolute temperatures between one end and the other. It's like, the thing about this is, you see, it does enable you to do certain things. I mean, for example, there was an exercise of a fisherman, and the expert in probability and statistics came to him and said to him, what's the biggest fish you caught in the last week? And he'd tell him how it was. Says, how many fish did you catch that were between the minimum weight, the middle weight between your highest catch fish, highest weight fish, and your lowest weight fish. And he'd tell him that over the last couple of weeks, and he'd come back and he could say to him, in 2 weeks' time, you're likely to catch this much fish, and it's likely to be this weight. And the guy was amazed because it was absolutely true. That was basically what happened. It's because he happened to give that data going back, and it was useful. That kind of projection was really useful. So I'm not saying this is totally useless, this kind of thing, because it is, these kind of statistical correlations and extrapolations and say regressions are very powerful statistical tools. But it's just in our particular case, I'm just looking at it from a customer's point of view and thinking, why did I pay this man or woman to do this work for me? So anyway, it's clear the line passes through the majority of the points. So at the farming, we're interested in how average temperatures are changing over time. So in the summary then, in this exercise, we learned about changing the cost function. So using different cost functions, we defined our cost function as well. Using can produce a different final result. You also learned how this behavior depends on these cost functions. They describe the best way to fit a model. Although from a data analysis point of view, there can be drawbacks no matter which cost function is chosen. Okay, so cost function is important because it decides how we're learning and the rate we're learning. So one of the most widely used learning, cost functions is to use to optimize the model by using this thing called gradient descent, which I tried to describe in mid-air yesterday using the shape of a oval sliced across, planted on the middle of the x-axis, which looks like a graph of y equals x squared, which kind of gives you that. And we will make our process move from the left side to the right side, down, 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 until the slope of our data point where we're moving is 0. And when the slope of something is 0, you've reached a straight line. The straight line, for example, the slope of that, as we saw with our trend line, when it was along the x-axis, was 0. That's our starting point. We started with a slope of 0. And in fact, in mathematical terms, you can find the turning point of any function, so the function where it changes direction from going down to up or up to down, by taking the equation of that line, differentiating it, which means finding the gradient of it, and making it equal to 0. And then if you do that, you can actually find the data point at which it will happen, the value at which that turning point will happen. So turning points are interesting, and that's what gradient descent is largely about, finding the turning point. So we're going to optimize our model using gradient descent. Now I want you to read this carefully in about 5 minutes to understand the process of gradient descent. It's a very commonly used optimization technique. It has a problem. It has a problem in that it can find local minima. So if your function isn't smooth, but let's say it's mountainous, it looks like a mountain, then what you think is a minimum is actually just a crevice. You've not actually reached the bottom yet. You've reached a local minimum with a kind of hill slope either side of you. So you think you're at the bottom, but actually you're not. You've just reached a local minimum. And that's the problem with gradient descent. That can happen. And there are lots of techniques that you can use to get yourself out of these local minimums. I'm not sure we'll get into those, but basically they all involve re-energizing the data point to see if it's possible to make it jump out of that local minimum. And if it is really the minimum, then giving it some energy to try and get it to jump out of it will simply have it come back down to where it was. But if it was a local minimum, like a crevice on the side of the mountain, if you jumped out, then there's a reasonable chance you might get out of that crevice and then be able to go down further. So that's there's all sorts of techniques to do that, but we won't get into those exactly. They're quite a kind of common sense type things to do that. But have a look anyway for the next few minutes. So this is where it talks about effectively undershoot and overshoot that I told you about as it goes from one value to another one. The calculus I told you about was the differentiation, but don't too concerned about that. Well, it does talk about local minimum. You can see that red line there on the local minimum. That means that you've minimized the cost, and it finds then the model parameter that actually minimized the cost. So you're plotting your parameter. I would specifically, you're plotting the parameter concerning with the slope. It's not going to really help you with the intercept so much, but it will help you with the slope. And we've got this shape here that if you change that parameter too much, starting it off at its first value, of course, the cost is going to be high. As you increase the value of your parameter, your cost is going to reduce. It then is going to hit a minimum, hopefully, and then it will start to increase again. So you know that the best value for your model parameter, the slope in this case, is at that minimum point there where the red line is. Because at that point, the cost is changing direction. The slope is changing direction from a negative into a positive. And when that happens, the point at which that happens is called a turning point or a local minima. And I say in maths, if that was a function, you would differentiate that function, set that differential equal to 0, because the differential gives you the slope. So, for example, if that was approximating a curve of y equals x squared, then that has two values. The differential is 2x. If you make that to be x equals 0, you will find that point. Okay, so this would have done a great job, as it says here. If parameters smaller than 0 or larger than 10 would have resulted in lower costs, like this image. So what's happened here is that let's say you were starting from the left, sorry, from the right, you would go down the slope. This is in the picture here with the double dip in it. If you were going from the right, you would travel down that slope thinking, yeah, great, I'm there, I'm getting better. Oh, I'm not getting any better. I must have found my minimum where that red line is. But in fact, that's not the minimum. What you found is a local minimum. There's actually a better minimum further on that you will find. So with our current algorithm, that would have stopped. It would have stopped at the point where the parameter was equal to 5 in that diagram. And that in our current algorithm, that's what would have happened. But what we really want is to find the real minimum, which is probably closer to -7 is what we really want to find. So our current algorithm would stop at that point for normal gradient descent. So you need to find some way, as I said before, of getting out of that local minima and then trying to jump up and find the next minima along in some way by giving the data point what is effectively some energy so that it can sample a lot further forward just to see is, yeah, okay, I'm here, I've found a minimum, but there might be one further on. So what I'm going to do is to try a few values quite far away. And what should happen is that it should get worse. But if I find a local minima and not the absolute minima, then it will get better. There will be something better along the line. And I can't do this step by step. There's an algorithm whereby I can project myself forward and try different values. So that's the first thing that's the problem. So in that preceding graph, the parameter value -7 would have been a better solution than 5 because it is a lower cost. Gradient descent doesn't know the full relationship between each parameter and the cost, which is represented by the dotted line, in advance. So it's prone to finding local minima parameter estimates that aren't the best solution, but the gradient is still 0. But it's not the best solution because it's not the best lowest cost. The other problem is instability. Related issue is the gradient descent sometimes shows instability. This instability usually occurs when the step size or the learning rate, the amount that each parameter is adjusted, is too large. So you get this continued undershoot, overshoot, undershoot, overshoot, and you never actually find the 0 point because you're undershooting and overshooting each time. Eventually you might get it because, as you can see, having a slower learning rate can solve the problem, but might also introduce other issues. First, slower learning rates can mean training takes a long time because more steps are required. Second, taking smaller steps makes it more likely that the training settles on a local minimum. So you stand much more chance of not getting stuck in a hole if you're moving really fast. It's a bit like if anyone ever plays golf and you're putting a golf ball towards the hole, if you kind of hit it too hard, even though there's a hole there, it will fly straight over the top and won't go down in the hole. And that's what's really happening here. You won't find the minimum because you might just go straight over it. You might just run over it like a train. So what tends to happen, so having a slower learning rate, yes, can do that. So, and by contrast, having a faster learning rate makes it easier to avoid local minima because the larger steps can skip over local maxima to do that. So as well, we'll see in the next exercise for each problem, there is an optimal step size, resulting in the optimum is something that often requires experimentation. So when we come back, we will play around with the parameters of gradient descent. in how we implement it. If we have the learning rate too fast, we have the benefit of not falling into local minima, but we might miss the actual minima completely, and the system is unstable. If we have two smaller steps, if we just go step by step by step, we'll fall into a hole. And once we're in a hole, it's quite difficult to get out. We might look into how we do that, but that's what the process of gradient descent is. Does that make sense? It's a very important machine learning tool, gradient descent, and it leads on to lots of other ideas. So having a good idea of how gradient descent works, you don't have to worry about the maths, just the common sense of it, then that's important. So a quick hands up before we go to the break, because I need to know whether we need to go back and look at gradient descent from a slightly different angle that might make it easier to understand. So let's have a hands up for our understanding of gradient descent, the problems of picking a smaller than optimum learning rate and a larger than optimum learning rate. They're the two things that we need to do before we look at what the optimum learning rate is. Just that at the moment you're aware of the issues associated with the two ways of doing learning. So a quick hands up, and then we can go for a break. Perfect. Just one more then.
Can't find my hands up.
Okay, that's fine. As long as it's a hands up, that's fine. Okay, good. So let's go to a break, and we'll come back in 20 minutes, and we'll look to see how we can find our optimum gradient descent parameters. I don't like gradient descent myself. I think there's smarter ways of doing it, but anyway, there you go. We'll follow this through because it's very good idea to have a good fundamental understanding. It's often a very a base point to get to where you want to go. The other technique, which we won't look at, is something called a pseudo inverse, and that finds it directly. It says, here's a matrix which describes all our data points. That's where we want to get them to go, and we can now define another matrix that when one is multiplied by the other gets you to where you want to go. So that's not by step-by-step descent, but that is actually by direct transformation. That's a very powerful technique for working out the weights that are applied in any kind of learning network. Okay, so back in 20 then. Okay, so I'll give you a chance to all get back together and then we will move on. So now we're actually going to look at implementing gradient descent. Let's hit continue at this point. So I've still got 30 minutes left, but I've only used 2 sandboxes. So here we go, gradient descent. Previously, we identified trends in winter temperatures by fitting a linear regression model to weather data. Here, we'll repeat this process by focusing on the optimizer. Specifically, we will work with batch gradient descent and explore how changing the learning rate can alter its behavior. Now, by a linear regression model, we mean of the form y equals mx plus c. So a simple gradient and a simple intercept is a linear model. The gradient allows proportionality directly to occur between one value and the next. It is possible to include higher order terms in your model. It still be a regression model, but you can then include terms, for example, of x squared and x cubed, as well as just a simple relationship between y equals x. You can have y equals x squared something, y equals x cubed something, and you can combine these in order to improve your cost function. All right. If it looks like, looking at your data points, that a curve might fit it better than a straight line, then we can look at other ways to fit those points. But for the moment, we're talking about a very simple linear regression with 2 parameters, the slope and the intercepts. So let's move on. So we'll load up our weather data again, as usual. We'll filter it to January, as usual, and make the adjustments so that dates are mathematically interpretable. So we get a fractional version of the mistakes. So that's pretty much doing what we did before, but we'll have to run it again. Okay, so that's loaded our data and prepared our model ready to go. And now we're going to obviously fit our model automatically. So let's fit a line to this data well by using our existing library. And as we can see, it's exactly the same as it was before. We're using importing this from statistical models and .formula API as a SMF. SMF could mean anything. And the OLS, which is the orthogonal least squared error method, we're applying given our formula of minimum temperature minus year, and then fitting the data. It's the plan, minimum temperature to year. They're the 2 things we're trying to relate together, and we're trying to get the best fit between them. And let's print the model. It should come out with 2 parameters, the intercept and the slope, as before, and we'll print them off and we'll see what we get. Now, this point here is asking us to print the slope and the intercept in this format. Okay, that's a format slope in this format, and we'll see what that format precisely is. Looks like 3 points of fixed point decimal. Let's see what we get. Yeah, so we've got 3 decimal places. That's what this 0.3f, 0.3f thinks it means, I think, 3 decimal places. And that's what we have. So we have our y, which is the result that we want. So we're trying to put in the year and predict the temperature. So this model will take our year, multiply that by 0.063, and then we will from that subtract 83.073, and we will then be able to go from our year to our predicted temperature. So that's our current model. Quite common for labels and features to be referred to as y and x. Y here is temperature and x is the year. This is the dependent variable, because that's what we're trying to predict. It's dependent because it depends on the experiment. X is the year. That's the independent variable, usually on the x-axis, because it's independent because we set the year independently of doing the experiment. The year is a value we set, and the y is the value we measure or predict. Okay, so minus 83 is a model parameter that acts as the line offset, and 0.063 is the model parameter that defines the slope, as we said before. So this little equation states that the model estimates temperature by multiplying the year by 0.063 and then subtracting 83, roughly 83. How did the library calculate these values? Well, let's go through it step by step. The first step, as always, is select the model. So we have this is exactly the same as we did before. And the model is to find the slope and the intercept. That's what it does. Okay. And that returns a string that summarizes the model. So we get a summary back and we get a prediction back, okay, of the different values. So we have to run that. And we get the message class ready. These system messages, they often exist in commercial systems for giving feedback at different stages during the development process. You wouldn't normally, in a product that was delivered to the customer, usually put those in, because the customer wouldn't want to see these intermediate stages. I can tell you a system I was working on, which is a very large multi-million pound system in Europe. Unfortunately, our development system was delivered to the customer, and it had a lot of these kind of messages in it. And as somewhere in the management I was given this message by our customer, and it said, obviously you often give status messages, and you can then put recovery messages, recovery from faults, recovery from incorrect data being put in, or out of range data, or something like this. So when you're writing your code, you just do as many checks as you can, so that if you have to debug it at a later stage, you can go through these reporting. And in fact, for my project, I'm going to get it to report every single decision that it makes in my project to some kind of log to say precisely where and why that decision was taken. That's an overhead I've decided to have. Anyway, what happened in this particular case, is the message I got was, dear Mr. Jacobs, we do not consider there are Klingons in the dilithium crystals to be a valid error message. And warp factor 1, Mr. Sulu, as being a recovery message. So that was a private coder who was obviously very much into Star Trek, one of the team. That was his private messages that he sent. He got his software to send to the screen, like this one here, model class ready. And unfortunately, that got to the customer. So I had some explaining to do in that case. Fortunately, the boss of the man that reported the problem to me was also a Star Trek fan. So we had a good laugh about it over a stein or two, and we moved on, which is what we're going to do now. So we're going to fit our model to gradient descent. We're going to use ordinary least squares, with the standard way to fit a line. Uses the mean of the sum of the squares of the differences, which is, it kind of makes sense because we did the sum of the square distances is our cost function. Yeah, our experimentation with the sum of the square differences in the last exercise. So we're going to replicate the preceding line fitting and break down each step as we can watch it in action. Recall that for each iteration, our training conducts 3 steps: estimates of y, calculation of the cost function, and adjustment of our model. So it's estimating the temperature from the year. We put in the year and we get back the temperature. We know a lot of values that are real values, our ground truth. So we can calculate our cost function between the estimation or prediction and the ground truth. And then we're going to adjust our model in some way according to this overall slope. So we can change our model by changing the slope. Note, we're not directly with this method affecting the intersect. Okay, the intersect value, that has to come later. So let's implement this now to watch it in action. Note, to keep things simple, we'll focus on estimating one parameter, the line slope, for now. We're not going to be looking at the intercept. I say that will come later. It's a kind of final polishing approach. So, as before, we're going to import numpys as NP. Just means we can use the shorter version, NP. Our X variable is the data.year. That's what we're saying. So as that data, the year field of our data that we've previously defined. And if we remember, our data is the mean of the around 1982, the range of years around 1982 as the center. Calculated that and put that in data. And our temperature true is initially what we're looking for is our data.minimum temperature. So we're looking for the minimum temperature that is predicted for a year that we put in. Okay, and that's our no, that's not a prediction value. That is the actual value from the data. So from the data set, we can take out the minimum temperature. And of course, that is our true value. That is our ground truth, the minimum value. So we're trying to predict that now. So we're going to choose our range of intercepts and slopes. The intercepts here, this is our range, line space. So as you can see, you've got a start and a stop point, which are these. And the slopes, again, we're not going to do the intercepts yet. That will come later. But our slope range, we're going to have from 0.06 to 0.07. And let's have a look at the last parameter there. So the third parameter is the 10th. So start, stop, and number. My guess is that's possibly the number of iterations that it's going to go down, or it might be the fraction of the error that it applies each time. Let's see what that is. But we've got the three values. So what we're saying is we think the slope is going to vary from minus 100. Sorry, the slope is going to vary from 0.06 to 0.07. That we think is the range at which we think our slope will exist in. And we think our intercept could be anywhere between minus 100 and minus 70. So we have to help the algorithm to start and stop at a certain point. So we're making the assumption that our minimum error is between those values, that our minimum error will occur with an intercept between minus 100 and minus 70 and a slope of 0.06 and 0.07. That's what our initial data, our initial investigation using a simple regression line has produced that. That's why we looked at the graph. We can look at the graph and say, what are the minimum and maximum values that this minimum is going to exist in? We know it's in there somewhere in that range. That's all the range that we saw on the curve itself, on the graph itself. And it's the same thing with the intercept. And so we're going to set this cost function. And again, it's the mean of the squared differences, which we've done before. And then we've got predicting the calculated cost, which will take our current value of intercept and slope, using the model to make a prediction and then calculate the cost. Predict the temperature by using these model parameters. So again, the estimate for our temperature for this go round is our X value, which is going to be the date, and our intercept. So the X value times the date, the date times the first value of slope, which is up here, plus the intercept. Now, slopes is a range of values. Slope is a particular value. Intercepts is a range that the intercept value can take. So just to make that distinction absolutely clear between those two variables. So predict and calculate the cost, we've done that, and then we're going to estimate it, and then we're going to return the cost, the function with our temperature estimate. So the call to the cost function, we return the cost function of our current temperature estimate. Okay. So this is basically saying this is what we think the estimate is, and this is how far out we are effectively. So we're going to return that, and then call the graphics method. This will use our cost function, which is above. If you want to view this code in detail, we can. So that's in graph or graphing.py. If you look in graphing.py, you'll see how the code works. It's a very straightforward graphing function looking at it. I like the idea that they've imported something like that rather than anything commercial, because it keeps it nice and simple. And we can look at graphing.surface. So we're going to have a surface plot now of X values, which are the intercepts, Y values, which are the slopes, and our Z value, which is going to be calculated Z value, which is the predict and calculate cost. So we're going to have an interesting kind of curve now. Look at a surface. So it's 3 dimensions. We've got the slope, the intercept, and the cost. Now, when you put those in together, we'll end up with something that will allow you to visualize where the minimum cost is. So let's run that. My sandbox run out. Oh, there it is. So this is our kind of 3D plot here. And we've got the cost in this axis here. The model slope in this one and the intercept here. So we're getting close to finding the minimum cost. Bear in mind, this is a surface, so you've got X, Y, and Z here. And so we want to minimize Z. Somewhere, let's get Z to be where Z is here to start with. So that's our, going down here is looking like our lowest value of Z. What do we think? Yeah, about there. So this is interactive. It's a nice plot. And dragging the mouse around, notice how the cost changes with both intercept and line slope. That's because our model has a slope and an intercept, which both will affect how well the line fits the data. Consequence is that the gradient of the cost function must also be described by two numbers, one for intercept and one for line slope. So that's why it is a surface plot, because the thing we're interested in, which is our cost, which we want to find as a minimum, is dependent upon which model slope is which slope the model uses as against which intercept. So there could be several points where that is a minimum cost, where that's there. Let's try and find the minimum cost. I think it's there, isn't it? Kind of 68. What's the minimum? Yeah, about 60. Yeah, I think you're right. About, oh, there's one. Yeah, and that point there, we appear to have 60, don't we? 60 and a bit. And that gives us a slope of 0.07, which is right at the end of our range, isn't it? So that's suspicious. I wonder if we should extend our range slightly, because it might, we only went as far as that. I don't like things that end when the range ends, because it could be nudging slightly further. But certainly the range of values that we put in for the intercept seems to fit. Minus 100 is within the range that we're talking about. So yeah, let's carry on. We might come back to extending that range a bit. So we can explore that. Our lowest point for the graph is the location of the best line location for a slope of 0.063 and an intercept of minus 83. Now let's try and train. Now obviously you had to work that out. 83. Slope of 0.063. Yeah, okay. And an intercept of 83. So that was probably, as we said, down there. Something like that, in that range, to find that. And we can implement the gradient descent now. So implement the gradient descent, we need a method that can calculate the gradient of the preceding curve. So we need to find something that can find the gradient of that. Now that is in three, that is something like, it's dependent upon two variables for the cost. So this calculates the gradient for a linear regression by using the mean squared error cost function, which we've done. So that's what we're looking at here, the mean squared error. That's what that's doing. And the gradient slope is, again, times the mean squared error of the error to each time. So we return the gradient intercept and the gradient slope So this is going to calculate the gradients of that curve over the range. So let's run that. Okay, so that function is ready. Let's move on to the next one. Now all we need to do is a starting guess and a loop that will update this guess with each function. Well, our starting guess we've got is 0 as a slope and minus 83 as an intercept. That's going to be our starting guess. They seem quite sensible. Minus 83 seem to be within our range that we looked at up here. Is our range of slope formula? So I'm looking for the range. Put in. Nope. Nope. Ah, there we go. So our range is 100 to minus 70. And that kind of figures with a starting point here of minus 83. That's what we got to. And we grab that information and we're giving it a slope of 0 to begin with. Let's see if that was in our original range. Well, not really. 0.6 to 0.7, that zoomed in. So we're being a bit cautious, looking kind of outside that. Let's see how it goes. Yeah. So we're going to start with the correct intercept so that only the line slope is estimated. This is just to keep things simple. Ah, I see. So we're going to learn, we're going to say that is the right value, 83 there. So given that value, we can now try and find this value here, the gradient, and that's what we're going to try and do. So we fix one thing, we fix the intercept at 83, and then we see what kind of slope we can learn and train to. That's what's happening here. So for I in the range, number of iterations, okay, calculate the predicted value. Predicted value is the number of iterations. Where did we set that? We set that to be number of iterations, maximum number of iterations to perform. See if we can find that.
It's in the down, so outside the gradient function, there is an indent changing.
Yeah.
So just in the last line.
I'm looking for where it sets them.
Last line, the same function, but the last line. So if you come down, yeah. So this is the last line. So this line does not belong to the function because it has indent left. So that is outside the function.
So we're setting the learning rate. Gradient learning rate.
Number of iteration is 1000.
That's equals there. I didn't realize that. Yeah, okay.
So
1000 then.
So this is actually outside the intent of gradient descent, and it's actually calling it. Yeah. It's calling the function. Okay,
so we've got 1000 then. Let's see how it goes. Let's run this. So we're fixing one. Well, it's doing what we did, which was to print it out every line. So this is our initial first go at the gradient, starting from 0, forward, 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 increasing in negative value until, is that terminated or is that just my screen?
I think it's terminated because the cost must be more now, because we can see the costs are decreasing.
And also it didn't print the cost, did it? And the cost came down at 60.32, which is roughly what we got in the graph.
Yeah,
we estimated the cost. So the cost is now zoomed in from here down to what we kind of fished out on the graph as being a minimum value of 60.32. Okay. So our model has found the correct answer, but it took a number of steps. Looking at the printout, we can see how it progressively stepped towards the correct solution, okay, by minimizing that cost as it went down. Now, what happens if we make the learning rate faster? So we take larger steps. So gradient descent learning rate 1E9, so number of iterations 200. So that sets the number of iterations to be 200 instead of 1,000. So we're taking only 1/5 as many steps. And the learning rate is 1E8. So that is how much you feed back each time. Let's have a look. Yeah, so the learning rate decides how much that you can change the slope by each time it goes around. Okay, so we fix that. And let's see what happens. We might end up with a worse result. Please activate your sandbox again. Okay, I've run out of time. Probably on my 3rd sandbox now. Okay, so we're going to run it with 200 now. Name error, gradient descent is not defined, so I didn't run. Oh, yes, I did.
I think it timed out, so it has deleted.
Oh, yeah, okay, so we have to run it from the beginning.
Might be, yeah.
I have to run it right from import numpy, no, pandas as well. Oh, dear. Okay, it's here, isn't it? Up to where it comes to pandas. Yeah, there it is. So I need to do that. Still waiting. Okay, and then I need to on that. Then I need to fit my model automatically. That's done. Then I need to, oops, done that. I need to now run that. Okay. That gives me my curve again. And then I need to implement gradient descent to find my values. That loads it first. There they go. And then I'm here with you. So now I'm going to do this. Name error, gradient descent not defined. Sorry? I need to do the one before. Let's try. Aha. No, that didn't work either, so I'll do the one above that. I think it might be here. That one's fine. And that one. Yep. Then this one.
I think run gradient descent.
Tried that. Try again. Okay. My model not defined. Oh, I need to go higher, much higher.
Steve, what is the first error we are getting?
The first error is my model is not defined now, so that's much higher up, isn't it?
Yeah, this one.
Before, yeah. That was before this.
Where the class model is there, I think below, little bit below.
Was it in this one?
Below, where will be class model, we're defining a model class.
I think it's before.
This one,
here you
I think.
Yeah, you could be right. From that. Right, now let's go straight to the end. Oh no, this has to be in order again, don't they?
The first.
They should be able to. There should be a setting where it reruns everything as soon as you open a new sandbox.
Yeah, I think the first error we got, which was that one?
Oh, I can't remember. Oh, it was because it didn't understand the.
So this is.
Let's see if we can get further. Gradient descent. That's working. Let's try this one.
No, I think there is the error.
Gradient descent. Okay, let's try again.
I think the one below also.
Yes,
okay,
it's working. It's all right. It's all right. Don't worry, you'll have this trouble when your sandbox runs out. Okay, so there we have it. We've got our estimate and our cost. As our starting point, that was our ending point. And is it worse or better? Our model appears to have found the same solution faster. If we increase the rate even more, things don't go so well. So we're now number of iterations to be 500. So that's the other way around, isn't it?
So I think
the learning rate is now
decreasing the learning
rate is now 5e to the minus 7. So that's much faster learning rate, isn't it? And let's see what that produces. Is it worse than 60? Is infinite cost? Yes. Because what's happened is it's hit instability. It's now been jumping side to side with that fast learning rate, and it can't find the hole, basically. That's what it is. So notice how the cost is getting worse each time. This is because the steps that the model were taking were too large. Although it would step towards the correct solution, it would step too far and eventually get worse with each attempt. For each model, there is an ideal learning rate, and it requires experimentation. And then we just fit one variable here to keep it simple. Expanding to fit multiple variables requires only a few code changes. We need to update more than one variable in the gradient descent loop. We need to do some pre-processing of the data, which we alluded to in earlier exercise, and we'll cover how and why in later learning material. So far, we have watched gradient descent in action, saw how changing the learning rate can improve a model's training speed, learning that changing the learning rate can also result in unstable models. You might have noticed that where the cost function stopped and the optimizer began, became a little blurred. Don't let that bother you. This happens commonly simply because they're conceptually separate and their mathematics sometimes can become intertwined. Yes, I wouldn't worry too much about that. Let's move to the knowledge check. Here we go. Have a good think about these. Quite interesting questions. I'll let you have a think about those and then we'll discuss them. Here are some academic papers for gradient descent. So I'll put these on files so that you can have a look at them. This is quite a good one. Large-scale machine learning with stochastic gradient descent. It's a good one to look at. So a good one. Exponential gradient versus gradient descent for linear predictors. Okay, someone's come up with another way of doing it and comparing it to gradient descent in that academic paper. In this one, an overview of gradient descent optimization algorithms, which we're going to look at just a little bit. But here's a really nice research paper. Looks on that. So it's a fairly live topic in research. Boosting algorithms as gradient descent. So this is talking about changing the number of elements there are in a particular classification. There's another paper here on accelerating gradient descent using predictive variance reduction, which is a parameter that's come straight from the data. Learning to learn by gradient descent So, okay, it's somebody applying gradient descent in a novel way. This is learning to rank order something using a gradient descent mechanism. So it's a nice idea of a cross-discipline usage of gradient descent. Long-term dependencies with gradient descent is difficult. Yeah, so gradient descent seems to be very kind of local. So this is looking at how you could extend that. And this, my particular favorite, is the tricks of the trade to actually really understanding how to optimize your gradient descent. And actually, it's unusual for an academic to use that word, trick, because it implies a less than serious approach. But I can assure you that this paper is quite rigorous in its outlook. Just so with the stochastic gradient descent, which a lot of these things are about, the algorithm is a drastic simplification. Instead of computing the gradient of the error, the cost and the function, exactly each iteration estimation to this gradient is on the basis of a single randomly picked value. So it is hoped that it behaves like its expectation despite the noise introduced by this simplified procedure. So instead of actually going through all of them, what you do is you say, right, I know it's in that value, that range. Instead of stepping from one at a time, let's just grab a few randomly and then see what that does for us and then decide what to do. So that's faster. I don't think we're going to be mentioning that in this course, but see why it might be faster, but it's less predictable because you're continuously taking a random shot at it. You don't really know how many random shots you're going to get. The safest solution, even though it's the longest solution, is quite a slow learning rate. So it depends if you're interested in, as ever with machine learning, is always a trade-off between accuracy and speed. Always the case. Okay, so let's have a quick look. What's the difference between supervised learning and unsupervised learning all together? Yeah, number 3. Supervised learning trains a model by comparing estimation to correct answers. The cost function for unsupervised learning doesn't need correct answers. Okay, so We'll look at this in future, but with unsupervised learning, you don't have labels. You have to look at the quality of your clustering in different ways. And there are several metrics, around 10, I think I'm using so far, to estimate the quality of a cluster without actually having any real values. It seems like magic, but it's actually quite true. So what is the role of the cost function in supervised learning? To maximize the cost, so the objective is reached. To calculate the cost by comparing estimates to correct answers. To update the model parameters. What do we think there? I think it's probably the second one. Do we think it's the second one? Yeah, I think it's the updating the model parameters is a different process. It uses the cost function as well as the original, the last value of the parameters. But I think probably we're going to go here for number 3 and here for number 2. And how does the gradient descent know how to update the parameters?
Steve, sorry, I was getting a bit confused on the second. Is this question correct? Should it be unsupervised? What is the role of cost function in unsupervised learning?
Well, the thing is, okay, the supervised learning trains a model comparing estimates to correct answers. The cost function for unsupervised learning doesn't need correct answers. The point is this: it uses a different method than actually having the correct answers. In unsupervised learning, you don't have any labeled sets and labeled data. You do not know the correct answers. It's very hard to know whether or not you've made the right selection in an unsupervised approach. I can show you I've got a really good paper on it. It's here. I can show it all to you if I can find it, if I haven't moved it already in my downloads. Let's have a look. Machine learning.
So the cost function.
Yeah.
So should it be in the unsupervised learning?
I see what you're saying.
So the second question. So
yeah,
I was
what it's saying. The second question here. The role of the cost function. Well, I think it's to calculate the cost, isn't it? By comparing the estimators to the correct answers, because that's working out the cost. So that will be the cost function. Let's see if we're right. It has something to do with updating the parameters, but that is using the cost function, not actually the cost function itself. So let's see when we get to the end. How does gradient descent know how to update the parameters? Does it compare cost for several combinations of parameters and then selects the best option? It uses an internal understanding of the relationship between the features and the labels to make intelligent choices. It uses calculus to estimate the slope of the cost function. And I think as we're talking about gradient descent,
the calculus?
That's what it's doing. It's finding the differential. As the differential changes, the differential of the slope, when that is 0, that's when you've reached your minimum. And of course, you would expect that differential to reduce as you move towards that minimum. Because obviously you start off high up on the left-hand side, nowhere near the minimum, and then you start moving forward, changing your parameter values, moving down the curve, and the slope is downwards initially if you're starting from the right-hand side, and the slope is actually faster, higher. The slope is higher at the beginning, and you keep going whilst the slope is reducing, until it gets to the optimum value here of our cost function. Let's get this clear. There's the slope of the regression line is not the same thing as the internal calculation of the slope of the cost function. The internal calculation of the slope of the cost function is how quickly the cost function is changing towards zero. And what happens is, obviously, just before you reach zero, the change is quite small. As you move further away from zero and you move up that curve, then the rate at which the cost function is changing increases as you go away from the 0 point. So what this system does, it uses calculus to measure how quickly the cost function is moving towards zero. And that tells you that it's moving in the right direction. So I think it uses calculus to estimate the slope. How many cost functions are available? A unique cost function is required for each processed currency or banking system. Cost functions help models process data and many types that are available. Different cost functions can arrive at different answers, and what's best depends on the goal. I think that's probably right, and also on the data as well. Okay, why is learning rate important? Speeds up or slows down training. It learns if the learning rate is too large or too small, it can prevent a model from being trained optimally. And both options are correct.
Yeah.
Both. I think it's both. I think the answer is 3, isn't it?
Yeah.
Can speed up or slow down the training depending upon what you make your learning rate. And if the learning rate is too large or too small, it can stop it being trained optimally. In the case of the learning rate being too small, it can find a local minima. And if its learning rate is too high, it can cause instability. And that's what we discovered. But both options in this case are correct. Let's see if we're right. You never know with these things. Yes. Hey, all the points. Put them in the bag. Great. Let's continue. So for a summary then, well done for getting through all that. Let's recap on what we learned. Supervised learning is a kind of learning by example. A model makes predictions. The predictions are compared to expected labels, and the models is then updated to produce better results. A cost function is a mathematical way to describe what we want a model to learn. Cost functions calculate large numbers when a model isn't making good predictions and small numbers when it's performing well. Gradient descent is an optimization algorithm. It's a way of calculating how to improve a model given a cost function and some data. Step size, or the learning rate, changes how quickly and how well gradient descent performs. Okay, so we've completed that module in that case. Well done. Let's have a look to see what we're going to be doing next. Okay, interesting. So that's where we're going next. I just want to try and find this paper for you, if I can. I may have sorted them. Already. I was doing this last week. Semi-supervised. Yeah, I've already put it in my archive. But it was an interesting paper talking about all the different ways that you could measure the quality of your unsupervised. So effectively creating a kind of pseudo cost function, which is kind of what that was alluding to. Oh, it's a bit of a shame I can't find that. Let's have a look. I usually label really good things with the words gold. Gold cluster metrics. There it is. Found it straight away. So internal versus external cluster validation indexes. Now, an external validation index is using labeled data. So sometimes you do have labeled data, even though you want to actually cluster, because you might find sub-clusters within the main classifications. So, and the internal ones are based purely on the structure of the clusters themselves. You don't have any labeled data. So this paper looks at both possibilities and comes up with all of these very strange looking algorithms. Kalinsky-Hurwitz, the Davis-Baldwin index, the silhouette index, which I find the most interesting. And again, these are the different indexes, internal, and these are the internal ones here. So these do not require labeled data to do this. Don't worry about the maths or anything. I don't understand it either. Well, I understand a bit of it. And then there's external ones, which are mostly called F-measure. And this is what we did F-measure. We talked about F-measure in terms of recall and precision. Yeah, so that wasn't just in Azure. That's a general term that's used throughout the whole of the clustering world. And it shows you directly how to calculate that. And purity, which is something I'm looking at the moment for my work, is another external measure, basically comparing what you predict to what the ground truth is, but in a kind of formula term there. So this is all real. And k-means clustering is one good method of clustering data. K-means, yeah, we looked at it. Yeah, that's one of the things we looked at, and it's one of the standard ways of checking it. The problem is finding K. One of my tasks in my project is to do just that on a large amount of data. So there you go. That's a real academic paper which you can find and read, and don't worry about the maths. Just try and read the common sense of what it's trying to say, and you'll learn an awful lot about what's going on. Okay, so let's make a start then for our next module, and then we'll continue it tomorrow. But let's make a start. So power of machine learning models comes from the data that's used to train them. Content and exercises, through content exercises, we explore how to understand your data and how to encode it so that the computer can interpret it properly, how to clean it of errors, and tips that will help you create models that perform well. So these are our learning objectives. We're going to visualize large data sets with exploratory data analysis, and then we're going to clean a data set of errors. Now, these are very important procedures. Errors like missing values, for example, values out of range, so they can't be handled, and predict unknown values using numerical and categorical data. So categorical data, the difference between a numeric value and a categorical one is that the numeric ones can be continuous, the categorical ones tend to be fixed. For example, shoe size is categorical because you don't normally get shoes of, it's interesting because in Europe, shoe size is numeric because you can have shoe sizes from 35 to 55 or whatever it is. But in the UK, we go for size 8, size 8.5, size 9, size 9.5, and 10. There is nowhere you can buy a shoe size of 10.2. So it's not a continuous data. It's not a single number. So that is categories in terms of numbers. But by what they're talking about here often is not categoric numbers, but categoric items. So if you're classifying something, you can say, right, all of those are shoes, all of those are socks, and so on. So these categorizing the data themselves into groups with similar features is another way of using categorical data. So there's two types of categorical data. There's discrete categorical data, meaning of the same type but with different values, but not continuous values. And then there are continuous data values, like from 0 to 100 in 0.1 steps. That's a continuous value. In fact, if it's in 0.1 steps, it becomes kind of categorical as well, because you've decided what the minimum step is. But if there's no minimum step, then it's a continuous variable. Okay, so let's begin. There's the introduction. Have a quick read. Last voyage of the Titanic. Excellent. Have a quick read of that, and then we'll move on. Okay, here's a scenario. As an eager marine archaeologist, you have an unusually keen interest in maritime disasters. Late one night, scrolling between images of whale bones and ancient scrolls about Atlantis, you come across a public data set listing people known to have been on the Titanic, its first and last voyage. Captured by the balance between fate and chance, you ponder, what were the factors that dictated whether a person survived this famous shipwreck? Data from the previous period is slightly patchy. A lot of information for certain passengers is unknown. You'll need to find ways to patch this up before analysing in full. So there's missing values that aren't in a sensible range, and so on. And before we can use it in any kind of modelling or machine learning, we have to tidy it up. We have to make it, but we have to be careful when we tidy it up that we don't introduce errors. And that's the art. The art is to tidy something up in a common sense, sensible way. And there are many ways of doing that. So we're going to start that straight away. Good, bad, and missing data. Have a quick read of that for a couple of minutes.
Sorry, Steve, you are on mute.
No, I was reading it for myself. So I guess we're close to the exercise there, visualizing the data. So ideally, we always work with complete data, but in practice, this isn't always realistic. When we have incomplete data, we can choose a model that can work with incomplete data, or remove the samples completely, the rows that have the incomplete data. That's what we did when we had the Visual Studio and Designer. We used data transformations to remove complete rows. Artificially add values that are missing with reasonable substitutes. You've got to think about what that might mean. I guess a reasonable substitute might be take all the averages around that missing point and use that average value for that missing point, assuming that making the assumption that the average value is a reasonable choice. There are other more sophisticated ways. In most circumstances, picking a model can handle missing data is best, though not always possible. Removing data is the easiest and usually a valid solution. Though care needs to be taken that removing data doesn't cause a sample to misrepresent the population. Again, adding data is usually a method of last resort. In the next unit, we'll work with our Titanic dataset, identifying and patching up incomplete data. Yeah, I mean, for example, if you had 10 parameters and one set of your data had really good, accurate data for 9 of the parameters, which you knew that was measured by a very, very good method, but they just simply had the missing value for the 10th parameter, then it might make sense, rather than deleting the whole rows, which it's got really good and representative data, rather than deleting those rows, it might be sensible to change your model so that it could handle that missing row. And it would look at the importance of the missing row compared to the rows that were present and decide if not including the missing row was going to produce a better model. So deleting the data is not always the best way, especially when you don't have much data to start with. If you've got 1 million records that are reasonably representative, and you've got 2 or 3 that have got some missing values, then yeah, no problem, just take them out. But if taking them out either takes out a representative section, as I've described, or key values, center values, that's going to make your overall results skewed in some way, then it's not a good idea. So it all depends on how much you've data and how good your data is as to what techniques you employ. So let's have a quick look at visualizing missing data. And then we'll get on to the real work tomorrow. We've got our sandbox, hopefully. We have to do it again tomorrow. I've activated my next sandbox. So as usual, we prepare our data sets to have data missing, which can cause problems when we perform machine learning. Missing data can be hard to spot at first glance. We've got passengers on Titanic, failed maiden voyage, and would like to try and figure out which kinds of things predicted whether a person would survive. Well, there weren't that many survivors. I think it was only 7 people that landed in the water, something like that. 1,500 people died. Our first task, which we'll perform here, is to check whether only 7 people that went into the water, I think, survived. The ones that went into the lifeboats, they survived. So just characterize what I just said there. So we're using pandas to load the data set. So there we go. We're going to install missing number. So this is some kind of depository somewhere that can do missing deal with missing numbers in data arrays. So here we go. That's a library function for us, a module or several modules that we can load in, and then we can get all the things we need, reading the data set into saying what the separator is for each one, and that the header is in 0, so that would be in the first row. That's what it's telling us there. That's given us some information as we read it in, and then we should just look at the first five values. This will give us the first 5 of our data set. It'll give us some idea of the parameters that are involved in deciding whether somebody survived or not. I'd imagine it was whether you were in first class. Oh, got nothing yet. Let's have a look. Go down a bit. Let's see. So passenger number 1 didn't survive. Oh yeah, it went down to passenger class. People tended to survive if they were in female 26. They paid that much money, no information on their cabin number, and they can embark either, I think it's either Southampton or what was the other place they embarked from? I thought it went from Liverpool. Oh no, it was built in Liverpool. Yeah, departed from. So there's our first elements, then. I even got the ticket number there. I can't believe that that's relevant. The fare is possibly relevant to survival. Okay, let's have a look at this data. Yeah, and now a quick peek of how many samples and columns we have. This gives us the shape of the data. So we've got 891 rows and 12 problems. So when you, in Python, when you type print dot shape, it's a good way of finding out what an array looks like. So just do the array name dot shape, and you will see it will return the rows and the columns. It's a nice way of quickly seeing the shape of something. You often see it in code as just a way of checking what the array looks like. So finding missing data, with data for that many passengers, 12 different variables. Do we have a complete data set? No. We know from our history there are more than 2,000 passengers on the Titanic. So we know straight away that we are missing information, more than 1,000 people. How can we tell whether what's left is complete? Well, we could print the entire data set, but this would be prone to human error and impractical with this many samples. A better option is to use pandas to report columns that have empty cells. But pandas is a very powerful array manipulation module or library. And here, using the isNull function, and then adding them all together in that data frame, we get our missing data. And we can rename a column heading here of empty cells. So we get extra information here. In our print missing data, we'll print off our empty cells. There we go. So the empty cells we've got no missing IDs. We've got 177 missing ages and 687 cabins. Now, the cabin number might be relevant if it decided what floor you were on. But the thing that decided mostly what floor you were on in the Titanic was the money you paid. If you paid lots of money, you were above deck in very warm and comfortable circumstances. The less money you paid, you went down in class to second class to third class, and your final class was steerage, which basically meant that you were in the real base of the ship and had almost no chance of surviving, actually, because of the nasty thing they did of closing all the gates off. And if you look at the data, you will see not that many survived from third class. Usually it's because they weren't actually in third class when it happened. if somebody was in their bed when it happened and they were in third class, they almost certainly died. So people did try and get out. There were not enough of anything, really. Unsinkable ship. And believe it or not, Titanic was all about global warming. Brings it back to date because of the El Nino that occurred just off South America at the time. It produced ice that went a lot further south than it usually did, and that's why they hit the iceberg, because it was a lot further south than it should have been due to early global warming. There you go. So we think. So let's visualize those missing data points just before we go today. So we're loading it up, and then, okay, Matplotlib is doing stuff. And here we have it. That's a really interesting one, isn't it? That shows you what data we've got and what data we haven't got. We've got reasonably complete passengers, survivors. It's the age and the cabin number and where they embarked upon. Now we know that quite well. And then we've got our summary here. This is really useful information. Okay, so we can identify individual passengers with the information here by looking at the data set for age, looking for is null, so information we don't know, so unknown age is here, and print only the columns we want to better fit the screen. So unknown age, and we're looking at the passenger ID, the name, survived, and age, and this here is limiting us to a number of characters, I think, or no, the number of times. So let's have a go. And here we have it. That's all the information. So it's exploring big data. We can list the passengers with missing cells or embarked information as well. So basically you can find out loads and loads of stuff just by manipulating those functions. I don't think we're going to get to cleaning up today, so I think we'll leave it there and restart it tomorrow, actually here. Okay, that's where we'll start tomorrow. Thank you for your attention today, and I'll see you tomorrow.
Thank you.
Thank you.
Bye.